Alright, so first of all, I would suggest that we draw a picture here. Um, we are worried about the tension in the rope. Now, um, we have this. First of all, let's look at the variables we do have. We have the mass of the bucket, which is 50.0 kilograms. We have the, um, we know the tension in the rope, or the force due to tension, can't be greater than 525 newtons. The bucket started at rest. It was lifted 3 meters. That 3 meters is our displacement, how far it moved. So we'll put our displacement as 3.0 meters. It is moving at 3.0 meters per second in the same direction as its displacement. Obviously, so 3.0 meters per second is going to be our velocity, or our velocity final, because that's what it's moving after it's been lifted 3.0 meters. We have a constant acceleration, but we don't know what the acceleration is, and we want to know if that tension exceeds 525 newtons. So drawing a picture of the bucket here, we know that it's accelerating upward. So my upward force must be greater than the weight. We have the weight of the bucket bearing down, which is Fg, and my upward force, since that rope is causing it to accelerate upward, has to be greater than the downward force, since acceleration points up. So my net force thus has to point up. So we know that the force of gravity can be found by taking the mass of the object, which is 50, times the acceleration due to gravity, which is 9.8 meters per second squared, or g. And we know that that is going to give us 490 newtons. So we know the weight of the bucket now is 490 newtons. So what we need to find is whether the upward tension is going to equal 525 or greater. And we can do that knowing the net force is going to be equal to the tension force, which is this upward arrow, minus the magnitude of the gravitational force. If you already called this negative 490 newtons because it's pointing down, then you would simply add the two forces. I'm just considering the magnitude. I know that my upward force points up, and I'm subtracting my downward force from it. However you want to think about that is fine, as long as you're consistent with in the problem. So the net force is obviously what's going to be causing our acceleration. We know that the net force is equal to mass times acceleration. So given that, we have that the tension force minus the gravitational force is equal to the mass times the acceleration. The problem is we don't know the acceleration, but using our kinematics from last chapter, we should be able to find it. We have a final velocity, a displacement, and we have an initial velocity because it started at rest. So let's use our kinematic equation that involves those variables. We have Vf squared equals Vi squared plus 2a delta x. We know the final velocity is 3. Square that equals 0, so that's going to cancel out. Plus 2 times a times delta x, which is also 3. So we get 9 equals 6a. So therefore, my acceleration is going to equal 9 divided by 6, or 1.5 meters per second squared. So now I have everything I need to solve to see if that tension exceeds 525 newtons. So the force of tension minus 490 newtons is going to equal the mass of that accelerating bucket, which is 50 kilograms, times the acceleration, which is 1.5 meters per second squared. So let's take force of tension equals 50 times 1.5, which is 75, plus 490. So that tension is going to equal 565, which unfortunately is greater than the rope. And if we keep to our sig figs, that should actually be 570 newtons, by the way. But it still, nonetheless, is greater than our 525 newtons. So that rope is going to be in danger of breaking. Notice we pretty much combined everything we learned so far. So you don't want to forget how to do those kinematic problems. We're going to keep getting practice. We're going to keep getting visits from past equations. That's just the nature of physics. We're trying to put everything together to solve these complicated problems with many steps, and a lot of thinking, a lot of solving there. So the final type of force we want to describe in this section is the normal force. Normal meaning the same thing as perpendicular. And that's going to occur anytime two objects are in contact with one another. They're going to exert a force on each other. And the normal force is in the perpendicular direction to the surface of contact. So you might want to say it's equal to the weight, but there's several cases where it's not. For instance, we take a look at this box. If the box is just sitting on the table, of course the normal force pushing up on the box is going to cancel out the weight. However, picture in the middle here, if you tie a rope to the box and begin to pull it upward with a force of 50 newtons, well, in that case, the table doesn't have to push up as hard. The normal force is only going to complement the force you're pulling on with the string. And those two forces together will cancel out the weight. Just like in your hand, if someone helps you by pulling that box up with a string, you're going to feel less force in your hand. The table and your hand are just objects. Just because one is living and one's not doesn't mean the laws of physics are going to change. The table doesn't have a feeling, but you can kind of think that the table feels less force if you're pulling up on it. And then the converse is true if you look at the right picture and you push down with 50 newtons. Now on the table you have the table has to support the weight of the box and the force you're pushing down on the box. So it's going to have to bear all of that force and push up with a much greater normal force, as you can see that large blue arrow in the right picture. And if you push so hard that the table just can't handle the force anymore, you might just end up breaking through the table. So that's the normal force in a nutshell, and we'll look at some sample problems on Newton's third law and how to calculate various tensions in normal force in class.